What specific computational bottlenecks and cost efficiency challenges does this paper identify when training small-scale language models, SLMs, on cloud infrastructure?
The paper identifies several computational bottlenecks and cost efficiency challenges when training small-scale language models, SLMs, on cloud infrastructure. Firstly, it highlights that flash attention is significantly more crucial for SLMs than for larger models, as it enhances the token-dollar ratio, particularly for smaller models where data movement becomes a bottleneck. Secondly, it notes that expensive hardware, such as H100-80 GB and A100-80 GB GPUs, is not necessarily cost-effective for SLM training, suggesting that more affordable options like A100-40 GB can be utilized without sacrificing performance. Additionally, the paper finds that distributed data parallel (DDP) is the optimal distributed training scheme for smaller models, while fully sharded data parallel (FSDP) is more effective for larger models, indicating a need for careful selection of communication schemes based on model size. Lastly, it emphasizes that maximizing GPU memory utilization does not always lead to cost-optimal training, pointing to the complexity of balancing performance and cost in SLM training.
How does the proposed method for analyzing and optimizing the training of SLMs work? Illustrate the process step by step, detailing any new techniques or algorithms introduced.
The proposed method for analyzing and optimizing the training of small-scale large language models, SLMs, involves a systematic evaluation of various hardware configurations and training strategies. First, the study identifies key metrics such as loss per dollar and tokens per second to assess training efficiency. It employs a grid search over different configurations, including GPU types, A100-40 GB, A100-80 GB, H100-80 GB, and communication schemes, distributed data parallel and fully sharded data parallel, to determine the optimal setup for each model size, 100M, 500M, 1B, and 2B parameters. Notably, the introduction of flash attention is highlighted as a significant technique that enhances the token-dollar ratio, especially for smaller models, by addressing memory constraints and improving batch size handling. Finally, the analysis reveals that DDP is preferable for smaller models, while FSDP is more effective for larger models, thus providing a comprehensive framework for maximizing training efficiency and cost-effectiveness in SLMs.
Can you provide a practical example, including numerical values, to demonstrate how the proposed metrics for $frac, text token, text dollar are calculated, and how this impacts the choice of hardware configuration?
To calculate the proposed metrics for frac, text token, text dollar, we first need to determine the cost of processing tokens in relation to the hardware used. For instance, if we consider a scenario where training a model on an A100-40 GB GPU costs 2 per hour and processes 1,000 tokens per second, the cost per token would be frac 2 text dollars, 3,600 text seconds, approximately 0.00056 text dollars token. Consequently, the frac text token text dollar metric would be calculated as a frac 1,000 text tokens per second, 0.00056 text dollars token, approximately 1,785,714 text tokens dollar. This metric significantly impacts hardware configuration choices. For example, using an A100-80 GB GPU may allow for larger batch sizes and higher throughput, thus improving the frac text token text dollar ratio, making it a more cost-effective option for training larger models compared to the A100-40 GB GPU, especially when scaling up to 32 GPS for larger models like 2B parameters.
What are the key findings regarding the performance of flash attention compared to vanilla attention in the training of SLMs, and why is this particularly significant for smaller models?
The key findings regarding the performance of flash attention, FA, compared to vanilla attention in the training of small-scale large language models, SLMs, indicate that FA significantly enhances the token dollar efficiency, particularly for smaller models. This improvement is crucial because in smaller models, the cost of attention is quadratic in context length, which becomes a dominant factor when the hidden dimension is reduced. As a result, smaller SLMs enter a data-bound regime where data movement between CPU, GPU, and GPU becomes the main bottleneck. Furthermore, for larger models, 1B and 2B, FA allows for the training of larger batch sizes, 1024, whereas vanilla attention leads to out-of-memory errors. Thus, the use of flash attention is essential for optimizing training efficiency and overcoming memory limitations in SLMs.
How does the study validate its findings? Describe the datasets, metrics, and experimental designs used to ensure robust conclusions about training efficiency and cost-effectiveness.
The study validates its findings through a systematic analysis of various hardware configurations and training setups using llama architectures, specifically focusing on models with 100M, 500M, 1B, and 2B parameters. It employs metrics such as tokens processed per second, frac, text token, text second, and cost per token processed, frac, text token, text dollar, to evaluate training efficiency and cost effectiveness. The experimental design includes running multiple trials, at least 3, for each setup, with each trial consisting of 10 training steps, allowing for the calculation of average performance and error bars. Additionally, the study explores different GPU types, A100-40 GB, A100-80 GB, H100-80 GB, and communication schemes, DDP, FSDP, across various batch sizes to assess their impact on training outcomes. This comprehensive approach ensures robust conclusions regarding the computational bottlenecks and cost efficiency of training small-scale large language models.
What limitations did the study encounter in its approach to optimizing SLM training on cloud platforms, particularly in terms of the generalizability of its findings or the scalability of its methods?
The study encountered limitations in generalizability due to its focus on specific hardware configurations, primarily NVIDIA GPUs, A100-40 GB, A100-80 GB, and H100-80 GB, which may not represent the full spectrum of available cloud platforms. Additionally, while the findings emphasize the effectiveness of flash attention and distributed data parallel (DDP) for SLM training, they do not explore other potential communication schemes or hardware types that could yield different results. The analysis is also constrained by the specific model architectures evaluated, namely llama models, which may limit applicability to other architectures or configurations. Furthermore, the study acknowledges that metrics such as CPU, GPU utilization, and memory bandwidth usage were not addressed, indicating areas for future exploration that could enhance the scalability of the methods. Lastly, the reliance on a fixed number of GPUs and specific batch sizes may restrict the adaptability of the findings to varying training scenarios in real-world applications.